So this morning I would like to briefly introduce you to carbon-carbon coupling reactions. We have to cover mostly the catalytic reactions which are unique, or rather celebrated and have some unique features. And so I would like to discuss carbon-carbon coupling first. The reason why this is important is fairly obvious. In organic chemistry, you put together large molecules using the retrosynthetic approach, and in the retrosynthetic approach, there are procedures for coupling two fragments which are carbon-carbon double bonded, but there are very few procedures for carbon-carbon single bond coupling reactions. So when the reactions that were discovered by Heck and Negishi and Suzuki became convenient to use, or when they discovered it and introduced it to the world, the chemistry world, it was quite a celebrated reaction, because these reactions were fairly easy to do and there are many variations. As I have indicated in this slide, only Heck, Suzuki and Negishi won the Nobel Prize. But the carbon-carbon bond coupling reaction could be carried out in a variety of ways. There is a Sonogashira reaction, there is a Stille reaction, there is a Kumada reaction, there is a Hiyama reaction. So the variations of these palladium catalyzed reactions are many. Almost all of them are palladium catalyzed. So that's another unique feature. So much so that in the 1980s to 1990, palladium was the most important metal, or the palladium was the most important element in organic chemistry. So this is something that was almost like a joke, because organic chemists mostly shun inorganic chemists and chemistry, and it turned out that palladium was extremely important for making carbon-carbon bonds. So with this statement, let me just tell you what Heck did. Heck reaction is very unique for a variety of ways. Heck himself was very unique. I'll come to that a little later, but he worked in an industry and he developed the reaction where you could make X, where R could be aryl or vinyl, or any Rx where there is no beta hydrogen. So there is no beta hydrogen on Rx, then aryl, vinyl, alkyl halides could be used. Halides are generally preferred, but triphlets are also good for this reaction. And the other fragment could be any vinyl species. So basically you need a hydrogen, a beta to the carbon where you're going to attach the R group. So we'll come to that in a few minutes. This reaction was so popular or so valuable that many pharmaceutical compounds were made using Heck, Suzuki and Negishi reactions, and that is the reason why they won the Nobel Prize basically. This is this is an example where you have a triplet group. So this is the Rx that we are talking about now, O triplet, and this is the vinyl group that we are talking about, and the hydrogen that is going to be removed, this is the hydrogen. Of course I have let me draw that properly for you. So this is the hydrogen that has been removed, and you formed a carbon-carbon bond between these two fragments. Notice that this is an odd, large cyclic ring system that has been generated, but they are proximal because of the way in which these molecules can orient themselves. It's not too difficult if you have a metal to bring this alkene close to the alkyl group that you're coupling it with. So the metal plays two important roles. One is the activation part and the other is the entropic advantage it brings by coordinating to the second fragment. So that's the value of this reaction. It's not always intramolecular like I have mentioned here, but intermolecular varieties are very common. Okay, so let me now proceed to the mechanism of the reaction. Basically, we are going to discuss 4 different reactions today, and almost all of them proceed through very similar pathways. All of them proceed through very similar pathways. And the active species is almost always palladium 0. Although the catalyst that is added to the reaction mixture can often be palladium 2. And because the ligand that is used is often a phosphine, and everything is just thrown into the reaction mixture, palladium 2, the phosphine, the substrates, etc. What happens is the ligand is capable of reducing the palladium 2 to palladium 0 by a simple reaction with, I'm writing a reaction which just a second, that was not what I intended. P double bond O plus 2H plus 2E. And this 2E reduces palladium 2 to palladium 0. So this is of course a very small amount that is needed because the catalyst can be in as small as 1% loading. The percentage of the catalyst that is added with respect to the substrate can be fairly low. So only 1% of the PR3 needs to be there in excess. And what happens is the palladium 0, when it is coordinated to a phosphine, is electron rich and undergoes an oxidative addition. The oxidative addition to Rx leads to a palladium 2 species, and this oxidative addition would be favored if you have electron rich Ln groups, and also if you have sterically large ligand systems, then the palladium complex that is available in solution in this form would be significant. If that is significant, then the formation of the square planar palladium 2 intermediate is quite plausible. Now, very often it is suggested that it is conjectured rather that the oxidative addition would give trans geometry if I have PDL2 species, and this rearranges to a cis. And the cis compound now has an option of losing one ligand, minus L plus alkene. So minus L plus alkene gives you another intermediate, which is denoted here. Now, the ligand that is lost in the reaction medium is not always the phosphine, because many a time you can use a chelated phosphine. If you have a chelated phosphine, then the loss of L would be highly improbable. What I mean is, if I have a system like this, then I'm not going to lose, if I'm not going to break this bond. Breaking this bond is going to be less probable. Maybe the loss of X group could be there. And here, this is where the solvent comes into play. A variety of solvents can be used in this reaction. There is absolutely no limit. It looks like THF, DMSO, you name it, quite a few solvents have been used. And so there is a variation in the reaction conditions that can lead to loss of X. In polar media, you can lose X. So that's loss of X will give you a positively charged species. So this is also a possibility. Both possibilities are there in this reaction. You can have a positively charged species like this. Now, you can have a migratory insertion of this R group onto the alkene. In order to do a migratory insertion reaction, the group that is the alkene has to slide to one position and stabilize a kind of, let's assume that this is, it's going to form an alkyl bond, right? So it has to form an alkyl bond by forming a metal carbon bond here. That's the new bond which is formed. So the alkene has basically slipped down a little bit, formed a palladium carbon bond. Instead of a pi bond, now you have a palladium carbon sigma bond. This is a sigma bond. Here you have a pi system which is interacting. Hope you didn't misunderstand me saying that this is a pi bond. This is actually a sigma bond only. It's a pi system that is interacting. So this is a pi system that is interacting. And here there is a carbon palladium sigma bond that is being formed. So this migratory insertion that is happening could have happened in the other direction also. meaning it could have moved from this R group, could have moved to carbon atom number 2. Suppose I say this is carbon atom number 1 and this is carbon atom number 2, then it could have moved to carbon atom number 2 also. That there is nothing that is really preventing it other than steric factors and the stabilization of the incipient positive charge, because you when you slide it like that, you will have an incipient positive charge being formed on the carbon, which onto which this R group has to migrate. So this has been studied extensively. Under what conditions do you have migration of the R group to the unsubstituted carbon or to the substituted carbon? Let me tell you that there are two, mostly it is governed by polarity of the solvent. So polar solvents, if you have polar solvents, then you have migration of the R group migrates to less substituted carbon. If I have non-polar solvents, then R group migrates to the CH2 group or the less substituted carbon. So this is something that has been observed. There is something for you to think about. Now, the sigma bonded intermediate that you have, has an option of going in the reverse direction. That means the migratory insertions, as we saw in other cases, in carbon monoxide insertion, for example, is a reversible reaction. So can this go back in this?
Yes, sir. Aren't the two things same that you have written, polar and non-polar? That less substituted and CH2?
Oh, sorry. Sorry. More substituted carbon. Yeah, sorry. Thank you for pointing it out. In this case, it's the place where the R group is present. Yes. Thank you. So, okay, where was I? Yes, I was talking about this sigma bonded intermediate. Migratory insertions are reversible. In principle, it could have gone on in this direction, but that would just give you the starting material or the previous intermediate. The more probable event is the abstraction of a hydrogen. The abstraction of a hydrogen in the beta position leads to the formation of an olefin complex. So the olefin complex could have palladium complex to R-R, then can give you decomplexation, or rather elimination of this olefin, falling off of this olefin, because it is now trans substituted. Its binding capacity would be less compared to the simple olefin, and elimination of HX is a reductive elimination. So you have oxidative addition, you have substitution. I have not written it as a substitution, but basically if one ligand falls away, it is a substitution reaction. Then you have a migratory insertion. Then you have a beta hydride elimination, which is basically the reverse of a migratory insertion reaction. And finally, you have a reductive elimination, which gives you back palladium 0 species. The palladium 0 species is then the catalytically active resting state of the molecule, catalyst. So this catalytic cycle, which we have gone through in reasonable detail, is repeated again and again in all these palladium catalyzed reactions. So after this, we will go through it fairly fast. The important thing is the role of the beta hydride elimination. The reason why we could not have any Rx for the first, for example, the first Rx, we said it's either aryl. This has to be aryl, vinyl, or an Rx without a beta hydrogen. Why? Because the moment you have a beta hydrogen, the palladium can do a beta hydrogen elimination and lose HX. So that is the reason why, and form an olefin complex. And that is the reason why we do not want such species. We would get from Rx, we will just do HX elimination, which is useless reaction. Useless in the sense, in this particular case, that's not what you want to do. So that is the limitation of the Heck reaction. Otherwise, you can have a variety of carbon-carbon coupling reactions proceeding with. And also the regiospecificity. Regiospecificity of this reaction. You can either have the R group migrating to the carbon, which is less substituted, that is the CH2 group, or the one which is more substituted, which is bearing the R group already. So both possibilities are there, and so that specificity is something that we need to control. Otherwise, you will get a mixture of products. That is another limitation of this whole reaction. So with this, we will stop our discussion about the Heck reaction. We will discuss some more reactions now. I am talking about the Suzuki reaction first, but I realized later that I should have introduced to you the Negishi reaction first. The reason is Negishi published a more general version of this reaction, which included the Suzuki reaction. But Suzuki kind of popularized this reaction where you have a boron substituted moiety. By the way, Suzuki and Negishi were both students of H.C. Brown. So you can see how Suzuki got this idea of using a boron substituted compound, for doing the Suzuki reaction. But Negishi, who is actually an HC, he turns out to be still a professor. He's taken over the chair, H.C. Brown chair professorship in Purdue University. So he continues in Purdue University. Suzuki moved to Hokkaido. It could be double K, it doesn't matter. Hokkaido University in Japan. And Suzuki decided to work with boron substituted compounds. These compounds are readily accessible from olefins. So you get olefins plus HBY2, you would get an RBY2. This RBY2 can now be added on to an RX with the same limitations that we are talking about. So the first step is in fact the same type of reaction that we are talking about in the Heck reaction. In these reactions, also a base is used. We'll see in a few minutes how this reaction works. And you get a coupling of R dashed in a very selective fashion with elimination of, in this case, by2x. Okay, we get elimination of by2x. So this is instead of mx. Mx is the general form that I've written here. So Suzuki reaction uses the boron substituted organic fragments for addition, whereas the Negishi reaction uses the zinc version. I'll introduce it to you a little later. Okay, so what are the advantages of the Suzuki reaction? Basically, like I said, it's fairly easy to get RBY2, and everything that we said about oxidative addition of the RX holds good here also. More often than not, you use the boron substituted compound. The iodine compounds are better for oxidative addition, but then, as you know, iodine compounds can be not so stable, especially they could be photochemically reactive. So the boron containing compounds are the most popular. X equals Cl has been made popular by Greg Fu, who has used some special catalyst additives of phosphines. He's introduced some bulky phosphines for carrying out reactions with X equals Cl. Otherwise, this reaction doesn't work. So Fu's innovations are required in order to do this reaction. As I told you earlier, the Suzuki reaction is just one variant of the general scheme which was introduced by Negishi. The other reactions are still a reaction and Sono-Gashira reactions. I'll give you those examples a little later. So one more cancer drug that was synthesized in bulk quantity using the Suzuki coupling. The key reaction was the formation of this carbon-carbon bond was formed, and the formation of this bond was facilitated by the elimination of BOH2X. How that happened, I don't know. So this is again something that is carried out by palladium 0. And notice the fact that they've used an inorganic base. Very often an inorganic base is better than triethylamine. Triethylamine can also function as a base. This can also function as a reducing agent. So sometimes people prefer triethylamine, but instead of using triethylamine, separation is easier if you use an inorganic base. Separation is easier. At the end of the reaction, if you want to remove the stuff that you do not want, then the inorganic base is easier because you just need to filter it. Whereas if I have something like triethylamine, then I'll have to do distillation, removing the triethylamine and so on and so forth. Okay. So what is this reaction? How does it work? As I told you, this is going to be very similar, so we will not spend too much time. The key difference, though, is the fact that you now have a transmetallation reaction and not a migratory insertion reaction. A transmetallation reaction happens in the second step. The first step, of course, is reduction of palladium 2 to palladium 0, palladium 2 to palladium 0, and adjustment of the ligand system around the palladium, which I have conveniently put as Ln. The value of N has to be low in order for oxidative addition to take place. Small values of N. If small values of N has to be there, then bulky ligands, if you remember our phosphine lecture, the bulky ligands tend to have smaller value of N. Now, oxidative addition will give you the same intermediate. So up to this point, everything that we discussed, maybe I should put the arrow here. Up to this point, everything is similar to the Heck reaction. And in fact, Heck and Suzuki and Negishi, everything will have the same pathway. Oxidative addition product that you have here can undergo a transmetallation reaction. The transmetallation reaction is nothing but a metathesis reaction. Only thing is it now happens with sigma bonds rather than with pi bonds. Let me just write it like as if it is Rm here. Then by doing a metathesis reaction, I'm changing the position of the sigma bonds from this position to this position. And I get a palladium R group, that's the R group which is present here, R group, and the MX, okay? So this MX, in this case, it is BZ2, BZ2 being, I mean, B, it could have been BOR2. So that's why we have written as BZ2 in this, at this position, at this point, at this place. So once you get PDRR, the species is just right for doing a reductive elimination of 2R, R dash of these two fragments. If I do a reductive elimination of these two fragments, then I get my product. So it's as simple as that. So what is the specialty? The specialty is that without the addition of palladium, you do not have activation of that X group and combination of the two organic fragments. So let me now tell you about the Negishi coupling. As I told you, the Negishi coupling and the Suzuki coupling are extremely similar. The only advantage in the Negishi coupling is that according to Negishi, Negishi was here in the campus several years ago, and one of the things that he mentioned was the fact that zinc compounds that he uses are extremely regio-specific. Unlike the Heck reaction, where you can have changes in the specificity, here there is only one type of coupling that happens, and so the reaction conditions are mild, and you can have regio-specific coupling. So he said that is the reason why he considered zinc to be better than the boron or the Heck coupling. Okay, so pretty much the catalytic cycle is the same, and I will tell you, I'll show you that also in a minute, but it's going to be exactly the same. But what I wanted to tell you was that the type of ligands that people use in both Negishi and Suzuki coupling, most of them are bulky groups. Okay, they are bulky groups. PPH3 is the most common ligand that is available in the laboratory, and so it would be something that is available off the shelf, and I have mentioned this here as a reference ligand, meaning that the first time you do a reaction, very often you would do it with PPH3 because that's the cheapest and the simplest. If the reaction works with PPH3, then you don't need to use more complicated ligands. For example, PTBU3, PCY3, and P2-furyl 3 are all ligands which are specialized ligands. You don't have to use those kind of ligands, and also they are more readily oxidized. They are more readily oxidized. So, and it's obvious by looking at the structure of these ligands, for example, that they are also more difficult to get. Okay. For reasons that would have been obvious to you, if I use a bidentate ligand, then I can force the X group to be a leaving group, and I have a positively charged species, and that positive charge changes the regioselectivity in the Heck reaction. So that kind of control can be there. So bidentate phosphines and monodentate phosphines are often compared. There are other ligands, like the ligand that is pictured here is a carbene, N-heterocyclic carbene, and N-heterocyclic carbenes are extremely electron donating, and so the electron richness of the palladium 0 becomes large. If that is large, oxidative addition becomes better. And if I have a large R group on the N-heterocyclic carbene, which is usually the case, then I have PDL or PDL2 at the max, even in the resting state. So what happens is the reaction is very facile when you have N-heterocyclic carbenes. Okay. So people, like I said, the type of solvents that one can use are extremely, the range is really large. You have on one end DMF, which is very polar, and you have toluene on the other end, which is extremely non-polar. So this is the situation as far as Negishi, Suzuki, and Negishi, Suzuki, and Heck reactions are concerned. The Negishi reaction has also been used for making pharmaceutical compounds, and that's the reason why when you have bulk drugs being made using these special reactions, they attracted the attention of the Nobel Committee, and so they had the Nobel Prize. So here in this case, it's a iodo compound and a ZnCl group which is eliminated. Okay, so this is done. Let me now tell you, okay, here's a table where a whole bunch of important natural products have been synthesized using these reactions. Okay, so this is just to tell you that how they really made their work valuable. One thing was the fact that this reaction was developed. The second thing was that they made sure that very valuable products could be generated using these reactions. So that was the reason why they really attracted attention. Okay. So the Negishi coupling is identical in terms of the reaction mechanism. The only difference between that reaction and the Suzuki reaction is that instead of BZ2, I have changed it to Zn. So M is now ZnY. Okay, M is now ZnY. So it's a fairly straightforward straightforward equivalence between Negishi and Suzuki. And as I told you, Negishi published a paper using boron even before Suzuki started using boron. So that's why Negishi was kind of hinting that he deserved the Nobel Prize more than Suzuki did. Okay. The Nobel Lectures are available in the website. I told you that Heck was originally in a company, and then he moved to University of Delaware as an emeritus professor, but originally he worked in a company, and then he retired and he was living in Manila, Philippines. So if you listen to the Nobel lecture, it's interesting that you find that Heck was living a very simple lifestyle. In fact, he was living in a village. He is living in a village, rearing a lot of livestock in the background, and he had completely given up chemistry after the end of his retirement from University of Delaware. Okay, so now I talked about Sonogashira reaction. Sonogashira reaction is also very similar. As I told you, the Hiyama reaction, the Kumada reaction, the Sonogashira reaction, the Stille reaction are all identical as far as reaction mechanisms go. The transmethylating agent is different. That is a major difference between these reactions. So I think the Kumada uses a nickel, and in the case of Hiyama reaction, silicon is used, and fluoride is used as a promoter. So let me. I don't think I have slides for these, but you can go ahead and Google these reactions. Hiyama, Kumada, Hiyama, Kumada, and Stille. Stille, I think I have already put down in one of the slides. So this is the Sonogashira reaction. The Sonogashira reaction couples an Rx with an alkyne, with an alkyne which has got a hydrogen. There is a limitation in this reaction, but notice the similarity between the Heck reaction and this reaction. Heck reaction had a hydrogen on a C double bond C. Okay, so this was a Heck reaction. The Sonogashira has a alkynyl group. Okay, so the advantage of the Sonogashira reaction is that they utilize copper salts which readily form acetylides. They form acetylides. And the acetylides, the formation of that is promoted by the presence of a base, and so you would have elimination of HX from the CUX and the base. Now this acetylide is undergoing transmetallation with this X group. So so the two groups that are undergoing transmetallation, let's mark them in green. So you have those two groups which result in the formation of palladium-2 species, reductively eliminate. So you have oxidative addition, reductive elimination, and the last step, regeneration of the palladium-0 species, and the catalytic cycle continues. So you notice that these reactions, as far as mechanisms go, they are pretty monotonous. They all have a ligand dissociation, and the ligand dissociation is followed by oxidative addition. Oxidative addition is followed by a transmetallation, The transmetallation is followed by a reductive elimination. Reductive elimination is followed by the regeneration of the catalytically active form of the palladium 0 species. So the variations that people have invented are primarily in terms of the ligand, which is the Ln. People have shown that if you use in coordinating sterically bulky ligands, you can promote some type of reactions which are otherwise not possible. Here is a Sonogashira example of a copper compound that is used. This compound is special. It does the same reactions that the Sonogashira, simple Sonogashira with the triphenyl phosphine would do, but the catalyst loadings are extremely small. Look at the catalyst loadings, 0.2% of palladium. Okay, and the phosphine amount is also very small, 0.4%. So the type of the type of innovation that people have made are mostly in the ancillary ligands that are present on the palladium. Okay, so I'll skip this also. Similar advancements have been made with palladium 0. But one thing I want to tell you about palladium 0, sorry, with the Suzuki reaction, and here the palladium 0 is the active catalyst, and the phosphines that people have used have been chiral phosphines. Chiral phosphines can lead to formation of chiral bi-aryl compounds. Now, as you know, the chirality in the coupling of two aryl groups would be quite difficult. The hindered rotation of these two are responsible for the generation of a pseudo chiral center here, and that is promoted by these phosphorus ligands, and these phosphorus ligands are chiral. So that has been studied. So asymmetric Suzuki coupling is something that has been, that's a special feature. Okay, aryl bond formation, the type of catalysts that have been, the ligands that have been used to do the catalysis. As I told you, chlorides can be used only if you have very, very electron donating and very bulky phosphines. And the way in which people have generated this aryl substituted palladium groups, aryl substituted palladium compounds through oxidative addition is by using most electron donating phosphines and sterically demanding. Now, if you look at the, I've already said this, but if you look at the type of phosphines that are generally used, they are like tricyclohexyl phosphorus groups. Okay, so here, of course, I've used nickel as a catalyst. So this is not the classic palladium catalyst, but this is like the Kumada coupling. Now, but again, the type of phosphines that are used are the bulky. Once the people realize that bulky and electron donating phosphines will do the trick, nickel has also been used efficiently, and it is definitely preferred over palladium because of the cost factor. Okay, so the mechanism of the nickel reaction has also been studied extensively, and it has been shown that unlike the palladium case where the rate determining step is the oxidative addition, in this particular case reductive elimination step happens to be the rate determining step. Okay, so it's not the oxidative addition, but it's the reductive elimination step which is the rate determining step. Okay. This has been done using linear free energy relationships. Like I told you in the beginning, to determine a reaction mechanism, one has to do substrate variations and look at how the reaction is going faster or slower in the presence of different substituents. And they've shown that the rate determining step is the reductive elimination step. Okay. Okay. To make compounds very electron donating, one option is to use a phosphorus ligand which is adjacent to a metal center. This is again something like anchimeric assistance. The electron density on the on the iron atom here seems to make this phosphorus a better electron donor. It seems to push the phosphorus to donate more electron density. I have already told you about Greg Fu from MIT. His contribution was basically the synthesis of some special phosphorus ligands which they have used in order to do the aryl coupling. Here I have in this slide the ferrocene substituted phosphine, which turns out to be a good electron donor. Okay, so I want to stop here because the type of innovations that have been done are I won't say they are incremental, but they are very similar. People have used variations in the phosphorus ligand or in the metal, but more often than not, still palladium is the best metal. There are substitutions like nickel can be used instead of palladium, etc., but they're not as good as this. Okay. I will give you one more example where a direct connection between the metal and 18 electron metal system and the phosphorus is used. This ligand is also a very good electron donor. As I told you in the previous example, the ferrocene was not directly connected to the phosphorus. Here it is directly connected to the phosphorus, and it makes it an extremely good electron donor. Okay, so I will stop here. These are reactions which you will find plenty in the literature. So with this, I'm going to stop and let's have some discussion about what any questions you might have on the palladium catalyzed carbon-carbon bond formation reactions. Okay, let me. Are there any questions on? Are there any questions or comments on the exam? Questions or comments?
Hello, sir.
Yes.
Sir, I have one question regarding the exam questions.
Yeah.
Please wait a second. Let me open the paper. Sir, I think others can go. I will just open the paper and ask you.
Can you post, if it is a very complicated thing, can you post it? Pankaj.
Yes, sir. I have a different question about the last class. So,
last class.
Yes, sir.
Which one was that? Which topic?
Sir, on the water lone pairs, two water lone pairs.
Oh, okay. That was the isolable analogy and isolable
yes.
analogy lecture. Yeah.
Yes.
Okay.
So there we talked about that in an isolated water molecule, there are sigma lone pair and pi. And
Yeah.
when it is going to interact with any molecule, it will combine and make two degenerate lone pairs to do that. So my question was, it seems like when there is a sigma lone pair and a pi lone pair, it looks like p lone pair and a sp2 lone pair. Is there any like are those same kind of thing, or can that be interpreted in this way?
I'm not. I'll explain this once again. Yeah. Oops. Yeah. So basically, you have in water molecule, in an isolated water molecule, you have a sigma lone pair, and the lone pair which you would have perpendicular to the plane on which, okay, this axis would be perpendicular to the plane on which the water molecule is sitting, right? Okay.
Yes.
So
yes.
this is these are the two. The problem is this is true only if you have C2V symmetry and you have a totally isolated system. The moment you have an approach of another M or another, say proton or anything else, then these two, which way would the proton approach? That is a question. Okay. So the proton, when it comes, it finds that it is, if it comes in between, it can mix the two and form a better donor orbital. That is the reason why you have H3O plus, which is having that angular form, and not one in which the hydrogen is attached like this, or the hydrogen is attached like this. Okay. So the moment you use this, yeah.
Yes, sir. You can complete it. Then I'll.
Yeah. So the hybridization basically improves the bonding ability of the oxygen with the incoming ligand.
So actually, I was talking about the analogy with the metal thing that we were discussing about. That when the hybridized orbitals are not combining with each other, the two orbitals with one electron each, the ML4 fragment that with that the analogy was taken with water molecule. So from that we can say the Mickey Mouse type of orbitals in H2O that are all not like combined, matching and mismatching. And after when the sigma and pi lone pairs are already generated, that means those are matching and mismatching combinations.
Okay. This was very artificial. I'll tell you how these two equivalent pairs were generated. They were generated. They are not real. Okay, not even. This came about because we started out by mixing six orbitals on the metal to match the L6 that was coming in, and then we artificially removed minus L2, minus 2L, sorry. Okay, and then we said there would be two orbitals. Actually, the 6 hybrids that are present on the ML6 are already a combination of S plus P3 plus dx squared minus y squared plus dz squared. Okay, they are already separated out. Okay, so this is only a thought experiment.
Yes, sir, I understood that. And actually, it doesn't happen like that. That
No, it
ML6,
doesn't
then
happen.
two ligands go out.
Yeah, we did it for our own convenience to show that there will be two orbitals which are free. Okay.
Okay, thank you.
Yeah. We can discuss that later. Anantu, you found the question or?
Yes, sir. It is the fifth question in the exam paper.
Fifth question. Okay. Can you read it out? Yeah.
Yes, sir. This is the bimetallic palladium complex.
Oh, okay, okay.
Yes, sir. You asked us to write the first step of the reaction, right? The first step of the reaction, wouldn't it be dissociation of the complex into two monomers?
Oh, I think I answered your question. This is a let me just see. This is the answer paper that I gave you, and you are saying this is which question? Fifth question.
Question number 5, sir. 5.
Question 5.
Yes, sir.
This one? No.
5, sir. The next one.
This
Yes, sir.
one?
This one. Yes, sir.
Okay, okay. What was the question? Now again, repeat your question. Dissociation of the ligand.
Dissociation of the palladium bond, sir. Like it forms a monomer, right? This is a bimetal center, so it forms a monometal center after heating, right?
No. Laws of chloride was shown. I mean, that's the first step that happens.
Sir, I mean, the reaction is basically the end product of the reaction. It's reductive elimination, right?
Reductive elimination, yes.
Yes, sir. So the first step will be dissociation and the next step will be reductive elimination.
Dissociation and reductive elimination. Dissociation is dissociation of the palladium chloride bond, surprisingly.
Sir, but in the lecture you have mentioned that when the reductive elimination takes place, it first forms a palladium monometal center complex, and then it undergoes reductive elimination to form a aryl chloride.
Did I mention that? I mean, can you
just... It was
just...
in the 11/12/2020 lectures, December 11th.
December 11th. I will check it, but I don't think that I would have mentioned that because this is the work done by Ritter. I remember that clearly, and I don't think I even vaguely remember saying it. I sometimes by mistake I jumped the thought, the pattern, and I might have said something wrong, but I will check it. 11/21. Okay.
There was a slide regarding that. Like there was a slide in which it was mentioned that first it forms a monometal center and then it gives reductive elimination product.
In this case, the chloride, if I remember right, the chloride dissociation was shown to be the first step. I'll check that again.
Okay, sir. Please check the lecture on 11th December.
Does that affect 11th December? Okay, fine.
Yes.
Yeah, I'll check that. Yeah.
All right, sir. Sir, also in the last question.
What about the last question?
That is the reaction of lithium-ferrocene with N2O4.
Yeah.
Do we need to write lithium nitrate as a product also? Lithium nitrate?
No. I just told you what is formed. I mean,
yes, nitroferrocene is the product, and then lithium nitrate will be the byproduct.
Yeah. Usually, I'm not asking you to. I'm not going to subtract marks if you don't write this, but then this is basically as chemists, I want you to always write every product that's very important. Okay.
Okay.
One of the things that you should always try and do whenever you do a reaction, make sure that you account for everything. Then you would have a much better handle on what is going on in the reaction. Okay.
Okay, sir. So also in the 9th question,
There was a mistake in the numbering. So 9th question. Yeah, this one.
Yes, sir. Yes, sir, that one.
Uh,
Sir, the delocalized pi bonds, how do we know whether it's a cationic delocalization or an anionic delocalization?
no, you don't know it. Only,
Yes, sir.
no, I said that here both are odd, both are open, both are terminal. So you can have attack on the terminal. And because of steric preferences, then I said that this is the preferred product.
Is that the exclusive product?
It turns out to be the exclusive product in the reaction also, if I remember right. I'll give you the reference if you want. But this is steric effects are the reason for the only difference between these two. It's not really DMG rules.
All right.
Okay. Okay, we'll close now.
Okay.
Yeah, thank you.